So here's another computer. And also, we're not dealing with two-dimensional space here. This is a three-dimensional random walk. The odds that you'll get from a target here to a specific target on the edge, this is a linear distance. As this increases, this random walk distance increases even more than you would expect on a two-dimensional random walk. And the random walks we're talking about for proteins are actually hyperdimensional. They're beyond 3 dimensions. They involve as many dimensions as there are characters in the sequence. I know I can't imagine that, but mathematically it's true. So here's a little bit of mathematics for the 2 letters. Define 2-letter words in the dictionary are 96, so the ratio is 1 in 7. And define 3-letter words as 972, so the ratio is 1 in 18. And so that's why you can get, with these fairly high ratios, interconnected sequences like this. I already told you about the statistics for 7-letter words. 7-letter checkerboard size is 8 billion, thereabouts. Meaningful 7-letter words in the dictionary, 23,000. So each meaningful word in 7-letter sequence space, or meaningful sequence, is surrounded by 347,000 non-meaningful ones. And we're not even talking beneficial here. We're only talking meaningful. So you keep going. Let's look at, he thinks it's like a weasel from Shakespeare. This is one of Richard Dawkins' famous phrases that he has this algorithm where his computer generates methinks it's like a weasel in a few generations. The checkerboard size for this 28-character sequence is 1 to the power, or 1 with 40 zeros after it. That's a huge number, or 27 is a 28 because there's he uses spaces, so that's another character for a sequence. So instead of 26 characters, there's 27, and methinks it's like a weasel has 28 characters in it. So it's 27 to the power of 28. That's where I get the 1 to the exponent of 40 there. So each square, if each square were 2 centimeters in size on our checkerboard, like yay big, right? Each square 2 centimeters in size, how big would the checkerboard be? The whole checkerboard for this sequence space. It'd be 1,000 trillion kilometers across, or 621 trillion miles. These numbers are huge. For example, how far is it to the sun? It's only 93 million miles to the sun, and it's only 25 trillion miles to the nearest star. So what's that in comparison to 621 trillion miles of our checkerboard? And this is only 28 character sequence space, okay? How many meaningful 28 character phrases are there in the English language system? That used to be a very difficult question for me, and I used to just kind of throw out big numbers. But I had really no basis to know how many there were, because you can't look it up 28 character sequences in the dictionary, right? So you have to kind of combine words and figure out how many would be meaningful, and then of those, how many would be beneficial. But then there's this paper that came out in 2000 where they estimated beneficial sequences in protein space, and they said that as sequence space increases by 27 to the n, and n is the size of the sequence, 27 is the number of characters. As it increases by 27 to the n, unstable sequences or non-beneficial sequences increase by less than 27 to the natural log of n, which means that there's a huge difference between the exponential of n and the natural log of n. You can calculate it on your own. But the result is that 28 character sequence space would only have 2 with 26 zeros after it of potentially selectable or even stable sequences, not even beneficial, just stable. And so the ratio there would be 1 out of 1 to 14. So for every stable sequence, there would be 1 with 14 zeros after it, unstable sequences surrounding it. Okay? In other words, each meaningful phrase would be surrounded by a vast ocean of 100 trillion meaningless ones. Okay, so how to get from one to the next? Changing 1 letter per second with no repeats, it would take over 3 million years to come across just one of the 1 trillion meaningful phrases on our checkerboard at 28 characters in size. So that's much different than our 3-letter sequence space. So what about increasing the population? This is just starting with one searcher, one guy walking around looking for targets in sequence space. But in reality, your population can be huge. You can have billions of individuals all walking around, and each of them can have millions of genes or genetic letters, and they can all be mutating. So does increasing the population help? Find targets? Yes, it does. But by how much? Take the same scenario as before, increase the number of evolving phrases to 1 trillion. This would search out sequence squares on our checkerboard 1 trillion times faster. This increase in population would practically guarantee a target sequence would be found in less than 1 year at our previous calculation. So this solves the problem, right? Have increase in the population, you can find it in less than 1 year, you solve the problem. Well, it solves the problem a little bit, but all you have to do is go step up the ladder of complexity a little bit farther and see what happens. How long would it take to find, for the same population of a trillion, all the bacteria on, or a trillion, which is all the bacteria on Earth alive today, to find a target in 1,000 character sequence space? It would take 1 to the exponent of 600 years, 1 with 600 zeros after it, using the same calculation, and that's just moving up to 1,000 amino acid sequence space or 1,000 character sequence space. And that's the math for those interested. It's also on my website. So Richard Dawkins to the rescue. He made this program on his computer where he took the same, he started with a random sequence, okay? And that's the starting sequence, and then he used the sequence and it made a bunch of copies of itself, or offspring, right? And then he selected the offspring that was the closest match to the sequence, not to the sequence, the closest match to me thinks it's like a weasel, out of all the offspring that he made from this one. And then he used that new sequence to make more offspring, and again selected the closest match for me thinks it's like a weasel. And within 40 generations, voila, he evolved me thinks it's like a weasel, starting with a random sequence. So has he solved the problem? Question. Which is more meaningful, Quizly-Gook or Quizly-Gut? In the English language system. Neither one, right? So if you start with blah, 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 and you go to blah, 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 which does nature select? Which is more meaningful? And it doesn't matter. I mean, if you change add another character that matches me, let's just say M-E, does that solve the meaningfulness? Is that selectable? Me, blah, blah, blah. Right? Is that meaningful that nature can select that? No. So Dawkins has completely skipped over the whole natural selection process. He no longer is using natural selection. He's using sequence template matching, which is not able to explain the origin of a lot of types of protein-based systems that exist in living things. So comparison to real life. Does the human language comparison actually correlate to what we see in real life? That's the question. So specified complexity. Kurathan again. The second major argument for intelligent design comes from William Dembski, a mathematician and philosopher who argues that nature is rife with examples of non-random patterns of information that he calls complex specified information, or CSI. To qualify as CSI, the information must be both complex and specified. The letter A, for example, is specified but not complex. You have just one little letter. It has to be A, but only A. It's only one letter, right? So it's not very complex. It's simple. However, a string of random letters, such as Squiffler, on the other hand, is more complex than just one letter of A, but it's not merely specific. Squiffler versus Skiffler or whatever could be anything, so it's not specific, a specific sequence. A Shakespearean sonnet, however, is both complex and specific. It's long, and it has to be specifically arranged. Okay? If Dembski were right, then a new gene with a new information system conferring a brand new function on an organism could never come into existence without a designer, because a new function requires complex specified information. This is Kenneth Miller's argument again. So are there any examples where random mutation combined with natural selection actually produces complex specified information of the level Dembski is talking about? Yes, there are. Nyelinase were shown to evolve by random mutations, completely random mutations. They found these bacteria in the back of a factory in Japan that produced nylon, and the bacteria on this pond all of a sudden started eating the nylon, using the energy from the nylon. And nylon is synthetic. It's not found in nature. So how did these bacteria evolve the ability, or develop the ability, to eat nylon? They did it with a frame shift mutation to a previous genetic sequence, which is like taking your hands on a typewriter and moving them over one spot, and then typing. And you type a random looking sequence, right? But this random looking sequence happened to be a functional enzyme that helped the bacteria eat nylon. What are the odds? Isn't that amazing that this frame shift mutation, this moving over your hands on a typewriter, would produce a random sequence that actually is functionally beneficial on a level that would produce nylon? That's amazing that it would just end on that. And it's fairly specific in what it requires. And it requires at least 200 amino acids, this enzymatic activity. Similar thing happened with lactase. This guy, Barry Hall, he's a scientist, and he wondered if he could take a bacteria that was able to digest lactase, or lactose sugar, delete the lactase genes from that bacteria, these E. coli bacteria, and then grow them in a lactose-rich environment and see how long it would take for that bacteria to re-evolve the ability to eat lactose, the sugar. And so he did this. He deleted the LacZ genes from E. coli bacteria, and he put them in a lactose-rich environment, and sure enough, they weren't able to digest lactose for a while. But in one generation, a small portion of the colony evolved the ability to eat lactose again. And they did it with a single point mutation. What are the odds that you're going to take one random step of the sequence space and end up on a lactose enzyme sequence? The odds depend on the ratio again. Well, Kenneth Miller says, aha, Dembski is falsified. His whole idea is nonsense because we have these examples of evolution in action producing novel functional genes that work.
Random question.
Basically, how long the generation lasts?
One generation.
Yeah, but how long is the bacterial generation?
20 minutes.
Yeah.
Okay. Same thing for antibiotic resistance. Bacteria evolve antibiotic resistance to antibiotics as fast as they come along, very rapidly, just about. In fact, that's a huge problem in medical centers, is that bacteria are able to evolve resistance to just about any antibiotic that comes along. But the question is, how does antibiotic resistance evolve? And to answer that question, you need to know a little bit about how antibiotics work. Antibiotics work by coming into a bacterium and attaching to a specific target within the bacterium. Okay, they attach to the specific target very tightly, and then when they disrupt the function of that target, then the bacterium either dies or is reduced in activity. So what happens if the target happens to get a small mutation and it sticks out a finger? Here comes the antibiotic. Can it attach very good? Can the target still probably work because it's only one little point mutation? The targets can still probably work, maybe not quite as well, but it can still work to do its original function, and it's resistant. So what are the odds that a single mutation will come along that blocks the activity or the binding function of the antibiotic? The odds are good. A random mutation that happens to put out little fingers on the target or whatever bumps on it that disrupt the binding of the antibiotic are very statistically likely to happen. That's why most forms of antibiotic resistance evolve commonly and very rapidly. Okay? Now let's move up to single protein enzymes like lactase, amylase, citrase, and whatever. They require no more than about 300 to 400 amino acids at minimum each. And so the odds that they will evolve is much less common. These examples do not happen nearly as common as these examples because in order to get these, you have to have an independent protein enzyme activity that's not based on the disruption or interaction with some other pre-existing system. These things function on their own, and so the odds that you're going to end up on a beneficial lactase or myelinase enzyme sequence are much less common, much more reduced. But given that they only require 300 to 400 amino acids at minimum, the ratio of lactases in sequence space has been estimated by those like Yockey and some other scientists, Sauer and Olson, and I have other references, at around 1 in 100 trillion. That's the ratio out of total sequence space. Even though this sequence space is massive, the number of potential lactases or sequences that would work as lactases is also massive, to the order of a ratio of 1 in, with 1 to the exponent of 14, or 1 to the 10 to the 14th or so. So let's say you have a colony of 100 billion bacteria. What are the odds that 100 billion bacteria will find a lactase within a single generation if the ratio is 1 in 100 trillion? The odds are reasonable. It doesn't happen all the time, but it happens often enough in a few types of bacteria where it's at least reasonable to happen in the total bacterial population of the Earth, which is trillion, or 1 to the 10 to the 30, or 10 to the 34th power. So that's why these systems are seen. But when you move on to systems that require at least 1,000 specified or specifically arranged amino acids residues working together at the same time, there's no example of such a level of evolution in literature. Evolutionary progress stalls out in an exponential manner, regardless of the maximum population you can reasonably think of in observable time. And statistically, when you work out the numbers again, this works into the many trillions of years.